Yeah. What's that?
Oh, the windows are closed.
Yeah, we could open them, but we don't have to. I feel like it might actually make it this somewhat more visible, so it's leaving closed. So the exam seem.
Oh, pretty good.
Yeah.
Wait, it was too hard.
Pardon?
I don't think it was too hard.
It's good. Yeah, I just looked at it. It looked reasonable. It's kind of like what I asked for. Um, yeah. So today we have or two tests to talk about. One is the P series test, and this stuff was taught you should have seen on Monday, I believe, in class. So more tests for the convergence / divergence of a series. The first one is the P test for a P series. And we'll talk about kind of how this can be modified. So here's the general idea or definition. Definition. Interesting. Let P be a positive constant. An infinite series of the form the sum from n equals 1 to infinity of 1 over n to the p, which looks like 1 over 1. Seems silly to write to the p, but I guess I'll write it. Plus 1 over 2 to the p, plus 1 over 3 to the p, and so on and so on and so on, is a p series. That's an excellent question, which we'll address shortly. And then I would say, since I'll add on here, we see that, yeah, if P is greater than 1, the P series converges. And if P is less than or equal to 1, the P series diverges. And so I feel like there's not a lot to say about the P series and the P test because it's kind of a very, it's one or the other, right? Like you look at it and okay, so here's a couple examples. We talked about one of these before. So example 1, the sum from n equals 1 to infinity of 1 over n to the first. This is the harmonic series. Equal to 1 plus a half plus a third plus a fourth and so on and so on and so on. And this series does diverge. It diverges because P is greater than or equal to 1. Specifically, P is equal to 1 here. We talked a little bit about this one either a class or two ago, where we kind of did this weird partial sum thing where we added up like the next power of 2 terms, and we kept doing that and seeing that, oh yeah, this thing's going to add up to being 1/2 plus 1/2 plus 1/2 plus 1/2 an infinite number of times. So definitely is divergent. And that'd be true for any power that's less than or equal to 1. Now, I would clarify a little bit here. According to the definition, the thing I'm about to write is technically not a P series. The sum from n equals 1 of 1 over n to the negative 2. I would point out that I would still call this a P series. I would say that P is equal to negative 2. Negative 2 is still less than or equal to 1. So this series still qualifies as being divergent under a P series. Now, really, what you really do is just rewrite it as the sum from n equals 1 to infinity of n squared. And then it's clearly divergent. The terms themselves are getting larger and larger and larger. Definitely the sum is getting infinitely large. So this is 1 plus 2 squared plus 3 squared plus 4 squared, which certainly diverges. And instead of saying it diverges as a P series, you can say it diverges by the nth term test. Because if we look at the limit of the sequence, the limit as n goes to infinity of n squared is certainly not 0. It's actually infinity. But that limit being not 0 means that the series diverges by the infinite test. I would also mention that if a series is convergent or divergent, either way, right? If a series has a behavior, you can add on or subtract off any finite number of terms and not change the behavior of that series. So for example, given that this series from n equals 1 to infinity of 1 over n diverges, we just said it before, you could literally start this anywhere. So does the sum from n equals 15 to infinity of 1 over n. Because if all of these terms add up to or diverge to infinity, well, I'm just writing the same thing less the first 14 terms. Well, those first 14 terms add up to a finite number. And if you take infinity, subtract off a finite amount from it, you still have infinity left over. So to answer your question from before, it doesn't actually matter where we start. If something is for a P series, although typically we only call it a P series if it starts at 1, which is a little bit annoying. But I think it's perfectly valid to say, for example, the sum from n equals 3 to infinity of 1 over n squared. Well, this is a P series or close enough to a P series, is convergent. Because we know that the P series from n equals 1 to infinity of 1 over n squared converges because P is equal to 2. which is greater than 1. And this series with a couple less terms in it also will converge. Most of the time when we talk about a series just having a certain behavior, it doesn't actually matter where we start. It does matter if we're talking about what the series converges to. So for example, well, I should say here, we don't know what this converges to. Well, that's not true. It is known what this series converges to. It's not something that we concern ourselves with in this class. So whenever we talk about a series being convergent or divergent, we only ever find what it converges to if it's a geometric series that is convergent. So for P series, we don't ever really find what they converge to. So if a P series is convergent, like the sum from n equals 1 to infinity of 1 over n squared, or the sum from n equals 1 to infinity of 1 over n to the fifth, or some other power that's larger than 1, like 1 over n to the, I don't know, 7.2. All of these P series are convergent, and we don't find what they converge to. Mostly because it's really hard. Like it's known what the sum of 1 over n squared converges to. I don't actually know what other powers these convergent series converge to. I don't know if we know if it's known what the sum of 1 over n cubed converges to or not. It's probably known, but I don't actually know.
Series negative values of that?
Yes, no negative values of n, not typically. I mean, technically they could. For example, we could certainly start off with, say, the sum from n equals -3 to infinity of something that we have to just make sure isn't undefined at some negative value. So I would think of a typical example being like a geometric series. So if we had, like, for example, 5 times 1/2 to the nth power, well, then I'm just starting a little further back than I normally would. That's going to be 5 times 1/2 to the -3rd, plus 5 times 1/2 to the -2nd, plus 5 times 1/2 to the -1st, and so on and so on and so on. And you can either find what the sums to by saying, well, we know that this part sums to a over 1 minus r, and then you could add on these parts here, which is 5 over 8 plus 5 over 4 plus 5 over 2. Sorry, that's wrong. That's 5 times 8 plus 5 times 4 plus 5 times 2. Or you could do what I recommend typically is that if a geometric series is convergent, doesn't matter where you're, well, I mean, it does matter, but wherever you start, whatever your ratio is, as long as your ratio is between -1 and 1, it's always the case that the geometric series converges to the first term of that series, whatever it may be, over 1 minus the ratio. So in this case, that's going to be 5 times 8, or I'm going to write 5 times 1/2 to the -3rd over 1 minus 1/2, which ends up being 5 times 8 over 1/2, which is 80. But yeah, so to answer your question, yes, a geometric series could start at a negative value of n. They just don't usually. Because you could always, I could totally rewrite this in a way just to get the same series, but starting at n equals 0. Check this out. We could rewrite this as the sum from n equals 0 to infinity of 5 times 1/2 to the, I really want my beginning power to be -3. So I'm going to say this is now going to be n minus 3. So I still get the same terms. So that's probably more likely what you would see. Usually people aren't going to write this, but we could. Okay, so P series, pretty straightforward. If your P is bigger than or equal to 1, sorry, if P is bigger than 1, we get convergence. If P is less than or equal to 1, we get divergence. It is important that you be able to write it just in this way. So for example, the sum from n equals 1 to infinity of, say, here, yeah, sorry, n. I was thinking of something here, and now it totally lost me. That's, yeah, what am I thinking here? Sorry about that. This is going to be fine. N squared over n. Sorry, my brain is just like not wanting to do it the right way. N to the p. What am I thinking? No, that's right. That's just, no, I don't know. Sorry, I was trying to make something up that seemed reasonable to me, and my brain was just like, nope, that's not going to work. Let's try that again. The sum from n equals 1 to infinity of 2 to the n over n cubed. Here's something that is not a p series. Even though we have a something divided by n to a power, if it's not 1 over n to a power or really a constant over n to that power, you can't use that kind of logic. I would point out the sum from n equals 1 to infinity of, say, 5 over n cubed is not exactly a p series, but we can modify it so it looks like constant multiples can be brought out in front of a summation. So we could definitely rewrite this as 5 times the sum from n equals 1 to infinity of 1 over n cubed. And then, oh, it is a p series. This is convergent. We see that our p value is equal to 3. And 5 times something that converges still converges. So yeah, the whole thing converges. This one, on the other hand, you could use the nth term test to see that this is divergent. I will just note here, the limit as n goes to infinity of the sequence 2 to the n over n cubed. Exponential things always overpower polynomial things. That's going to grow to infinity, which is certainly not 0. So we get divergence. What about something like, if we go here, what about the sum from n equals 1 to infinity of n squared over 2 to the n? Well, it's not a p series. It's not a constant over n to a power. It's also not geometric. So not a p series. Not geometric. The nth term test isn't going to help us here, because if you do the nth term test, the limit is going to be 0. The limit as n goes to infinity of n squared over 2 to the n does in fact equal 0, because the exponential thing is in the denominator and it's growing faster. So we need something new. So let's back up for just a second. I want to talk about geometric series for just one more minute, because we're going to use it here. So let's say we had this series, 24 plus 12 plus 6 plus 3 plus 3 halves plus 3 fourths, et cetera, et cetera, et cetera. I think the ratio is relatively obvious, but since you're the person here, Heather, let me ask you, is it obvious what the ratio is? So here's the way we can always find the ratio. So I should say, if it's geometric, which maybe it's not, maybe I wrote something that's not actually geometric, but if it is geometric, we can always find the ratio by dividing a term by the previous term. So if we take this second term divided by the first term, we get 12 over 24, which reduces to 1/2. And the same thing is true here, right? If we look at 6 divided by 12, or a3 divided by a2, we get 6 over 12, which is also 1/2. Same deal here. a4 divided by a3 is 3 over 6, which is 1/2. So if you can keep, we don't really need to keep doing it, but we could, and every time we did it, we'd get 1/2. So we can kind of see here that no matter how far out we go, right, that the ratio is always going to equal the next term divided by the previous term. So A2 divided by A1, A3 divided by A2, A4 divided by A3, or if we keep going, sum A sub n plus 1 divided by A sub n. For geometric series, this ratio will always be the same value every single time. Something just happened to my video here. That's weird. I think I was gesticulating too. Wow, let's see if we can fix that. Interesting. Let's try. Yeah, weirdly. One moment. Just getting to the good part too. Okay, let's try that again. Let's open you back up. Okay, good. There we go. All right, back in business. Maybe. Sorry. Why'd you go over there? Okay, let's try this now. Cool. All right. So let's look at this other series that I was talking about. And we're going to kind of look at the same idea. So for this series, the sum from n equals 1 to infinity of n squared over 2 to the n. It's not geometric, but we're going to kind of observe it to be similar to geometric series anyway. So let's write out some terms. We're going to get 1 over 2. We're going to get 2 squared over 2 squared. We're going to get 3 squared over 2 cubed. We're going to get 4 squared over 2 to the 4th. It doesn't seem like these terms are really like that interesting yet. But if we go way further out, and I just point out, these are not geometric, right? That's equal to 1. That's equal to 9 over 8. That's also equal to 1. The next term would be 5 squared over 2 to the 5th, which is 25 over 32. But if we go out to say like the 100th term and the 101st term, so the 100th term is going to be 100 squared over 2 to the 100th power. And the 101st term is going to be 101 squared over the 2 to the 101st power. So there's our a sub 100 and our a sub 101. And let's look at the ratio of those two terms and see what happens. So if we look at a sub 101 divided by a sub 100. Okay, let's see here. So we've got 101 squared over 2 to the 101st power divided by 100 squared over 2 to the 100th power. I will say that when we do these ratios like this, we often don't write this initial fraction. We often write the top thing multiplied by the reciprocal of the bottom thing, just because we always end up doing that. So here's what we've got. We've got 101 squared over 2 to the 101 times 2 to the 100 over 100 squared. And then we usually rearrange the fraction so that the similar things are together. So we have 2 to the 100th power over 2 to the 101st power times 101 squared over 100 squared. Now check this out. 2 to the 100 divided by 2 to the 101st, well, you have one more 2 on the bottom. So that's really going to be a 1/2 times, and look at this. 101 squared over 100 squared, you could actually do the division first and say that's really 101 over 100 squared, which is 1.01 squared, which is almost 1. This is actually equal to 1.0201. But essentially, this whole fraction is pretty close to 1/2. It's a tiny, tiny, tiny bit bigger than a half. And if we went even further out, we would see the same thing happening. Like if we looked at, say, the 1,001st term divided by the 1,000th term, you would get something like 1/2 times 1,001 over 1,000 squared, which is even closer to 1/2. So in essence, if you go far enough out, this looks very similar to a geometric series whose ratio is 1/2, which in essence means that this series is convergent because it's essentially a geometric series whose ratio is 1/2. So what this leads us to is essentially the idea of the ratio test, which is that if eventually the terms act like a geometric series with a ratio that's less than 1, we can conclude that the series is convergent. So the ratio test says the following. If the limit n goes to infinity of the n plus 1 term divided by the nth term, and I think we need an absolute value here, although it's usually not that important. Sometimes there's an absolute value there. I think there usually is. But again, most of the things we deal with are already always positive. So if this limit, which we're going to call L, if this limit is less than 1, then the series from n equals wherever to infinity converges. And similarly, if that limit as n goes to infinity is greater than 1, then our ratio is greater than 1 and the series is divergent. And then sadly, if the limit is equal to 1, the test is inconclusive. So if the limit as n goes to infinity of an plus 1 over an is equal to 1, what that really means is you should try something else. Then try a different test. So what we can say here for this previous example, actually writing it out, is that, can I maybe? Sure. So for the sum from n equals 1 to infinity of n squared over 2 to the n, if we apply the ratio test and take the limit as n goes to infinity of the n plus 1 term over the nth term, that's going to be the limit as n goes to infinity. So watch how we do this here. The n plus 1 term is n plus 1 squared over 2 to the n plus 1. Instead of dividing by the nth term, we're going to multiply by its reciprocal. So we're going to multiply by the reciprocal of n squared over 2 to the n, which is 2 to the n over n squared. And you could write absolute values here, but everything is already positive, so you don't really need to write them here. It doesn't change anything. So then we're going to simplify this. We're going to put the like things together. So I'm going to put the n plus 1 squared over the n squared and the 2 to the n over the 2 to the n plus 1. I'm going to simplify just a little bit. I'm going to write this as n plus 1 over n squared, and 2 to the n over 2 to the n plus 1 reduces to just 1/2. And then using those rules about limits and having the same degree, n to the first plus 1 over n to the first, the limit of that is just 1 over 1 squared, still 1. So we end up with 1 times 1/2, which is 1/2, which is less than 1. So that means our series converges. So when should we use the ratio test? A good rule of thumb, well, first of all, if it's not a geometric series, if it's not already something you can use a different test for. So it's not geometric, it's not a p-series, and the nth term test yielded to 0. The other things we should look for are either something being raised to the nth power, like here, or having an n factorial. Those are both good signs that the ratio test is going to easily apply. So for example, keep me to write things here, or something raised to the nth power. So like in this previous one here, we had a 2 to the n. That was a good sign that we should be using the ratio test. So here's another example. The sum from n equals 2 to infinity of n to the 4th times 3 to the n plus 1 over n factorial. So this is meeting both of the things I'm looking for. I have an n factorial, and I also have something essentially raised to the nth power. 3 to the n plus 1 is really just 3 to the n times 3 to the first. So that's a something to the nth power. So let's apply the ratio test. So we're going to do the limit as n goes to infinity of our n plus 1 term. So we have n plus 1 to the fourth times 3 to the n plus 1 plus 1 over n plus 1 factorial multiplied by the reciprocal of my a sub n, which is just the thing that's right there. That's going to be n factorial over n to the fourth times 3 to the n plus 1. And then whenever you do this, I would always rewrite it as fractions where essentially similar things are quotients. So I'm going to write this as the limit, as n goes to infinity, of I want the n plus 1 to the fourth over the n to the fourth. And I want the 3 to the n plus 2 over the 3 to the n plus 1. And I want the n factorial over the n plus 1 factorial. Because if we group these things with the like things, we can simplify each of them. So then, well, some of them anyway. So we'll limit the n plus 1 to the fourth over n to the fourth. Whenever you have things raised to a power like this, we're just going to combine them into an n plus 1 over n to the fourth power. And eventually, when we evaluate this limit, that part's going to be 1 for the same reason this part was 1. 3 to the n plus 2 divided by 3 to the n plus 1 is 3. Right? If we subtract those powers, n plus 1, n plus 2 minus n plus 1 is just 1, so the power is 1. And finally, n factorial over n plus 1 factorial. This is one where you have to be a little bit careful. I kind of like to think of it with just a numerical example. So if I had, for example, 5 factorial divided by 6 factorial, what does that simplify to? What do these things even mean? 5 factorial means 5 times 4 times 3 times 2 times 1. And 6 factorial means 6 times 5 times 4 times 3 times 2 times 1. And we can see that almost everything cancels except for the 6 in the denominator. So this reduces to 1/6. Another way you can see this without writing quite so much is that 5 factorial over 6 factorial is equal to 5 factorial over 6 times 5 factorial. And then you can cancel the 5 factorials and get a 1/6. So the same idea here, I'm going to rewrite the denominator as n plus 1 times n minus 1 times n minus 2 times n, but I'm not going to write that. I'm going to write n factorial. And then those n factorials certainly can cancel. N factorial divided by n factorial is just 1. So then rewriting this, I have the limit n goes to infinity of n plus 1 over n to the fourth times 3 times 1 over n plus 1. I suppose if I really, really wanted to, I could cancel an n plus 1 here and one of the n plus 1s on the top there, but I don't really need to do that. Here's what's going to happen. The limit of this part is 1 to the fourth times 3 times the limit of that part is 1 over something infinitely large into 0. So we get 1 times 3 times 0, which is 0, which is less than 1. So we get convergence. Let's look at a couple more of these because they do get a little bit like that. Let's look at sum from n equals 3 to infinity of 4 to the n over n cubed plus 2n. Same idea. So if we use the ratio test here, we're going to see something, well, we'll see something a little different. So we're still just starting off the same way as ever. It's always the limit as n goes to infinity of the n plus 1 thing over the n thing. That's going to be the limit as n goes to infinity of 4 to the n plus 1 over n plus 1 cubed plus 2 times n plus 1. Kind of gross. Times the reciprocal of that, which is n cubed plus 2n. I'm going to do the same thing I did before. I'm going to rearrange it so the like things get kind of put together. I'm writing this as limit as n goes to infinity of 4 to the n plus 1 over 4 to the n times n cubed plus 2n over n plus 1 cubed plus 2 times n plus 1. You might do one simplification here, or just note that 4 to the n plus 1 over 4 to the n is equal to 4. So our limit's going to be 4 times the limit of this. I don't really want to multiply this out. Neither do you, typically. I'm going to observe that on top, my highest power of n is n to the third. My coefficient is 1. And on the bottom, if I were to multiply that out, I would get a 1n cubed as my highest power of n as well. So the limit of that part is going to be 1 over 1. If you really, really wanted to, you could multiply out the bottom here. The bottom would multiply out as n cubed plus 3n squared plus 3n plus 1 plus 2n plus 2. And then you can combine terms and get n cubed plus 3n squared plus 5n plus 3. But notably, your highest power of n is n cubed and its coefficient is 1. So our limit ends up being 4, which is greater than 1, which means this series diverges. Let's do that. Yeah. Here's a fun one. Let's do this one first, actually. The sum from n equals 1 to infinity of 1 plus n over n squared. Okay, what I want to point out here is this does not have any of the hallmarks I look for when trying to apply the ratio test. If we apply the ratio test, it's actually not going to work out for us. It's going to be inconclusive. Let me show you. So actually, more generally, if your series from n equals whatever to infinity is a polynomial in n over another polynomial in n, like just powers of n and no other things, no exponentials, no factorials, the ratio test will never work for this. Let's see why. We do the limit as n goes to infinity of my n plus 1 term, 1 plus n plus 1 over n plus 1 squared, times the reciprocal of my original nth term. Looking at this here, look what I've got. With a limit as n goes to infinity of n squared over n plus 1 squared. The limit of that part is going to be 1. And n plus 1 over 1 plus n, or n plus 1. The limit of that part is also going to be 1. You're always, always, always going to get 1 when you do the ratio test for a rational function like this. So we never use the ratio test here because it's never going to work. Instead here, what we could do is we could break it up. We could rewrite it as the sum from n equals, I should write here, sorry, inconclusive. The ratio is equal to 1. Here, I can break it up as 1 over n squared plus n over n squared, which I can then write as 2 summations. The sum from n equals 1 to infinity of 1 over n squared plus the sum from n equals 1 to infinity of 1 over n to the first. This first series here, is this first one, the sum from n equals 1 to infinity of 1 over n squared, is that one convergent or divergent? Yeah, it's a convergent P series. Convergent P series because P is bigger than 1. What about this second one here? Is this one convergent or divergent? It's actually divergent. So the power is 1 over n to the first, and my P equal to 1 means the series is divergent. Divergent P series Because p is exactly equal to 1. Also called the harmonic series.
So. Oh,
So what does it mean overall? It means the whole thing diverges. Because if you have a divergent thing plus a convergent thing, well, the convergent thing just adds up to some finite value, but the divergent thing is still diverging even if you add 7 to it. So this is overall divergent. On the other hand, just because I think it's kind of a neat example, if our example had been, say, for example, the sum from n equals 1 to infinity of 1 plus 2n over n cubed, you could also break this one up in the same sort of way and write it as the sum from n equals 1 to infinity of 1 over n cubed plus the sum from n equals 1 to infinity of 2n over n cubed, and then rewritten that second part as 2 times the sum from n equals 1 to infinity of 1 over n squared. And then both of these are convergent because they're both p series with p bigger than 1. That converges. And if the two things added together converge, it's the result is also. So this is definitely convergent. Got one more. Well, I got lots more examples, but I got one more example I want to do, especially because I think it's kind of fun. If I can remember it. Yeah. So we want to find the sum. N equals 1 to infinity of n factorial over n to the mth power. This is definitely a time to use the ratio test. You've got all the things you want, but it's going to be a little bit weird. So we're going to the limit of the ratio test as n goes to infinity of n plus 1 factorial over n plus 1 to the n plus 1 times n to the n over n factorial. And just like every other time we've done this, we're going to combine the like things in fractions. So we're going to rewrite this as the limit as n goes to infinity of n plus 1 factorial over n factorial multiplied by n to the n times, over n plus 1 to the n plus 1. The n plus 1 factorial over n factorial, we're going to rewrite. And set the limit as n goes to infinity of n plus 1 times n factorial over n factorial times n to the n. And in the denominator here, instead of writing n plus 1 to the n plus 1, I'm going to write n plus 1 times n plus 1 to the nth power. Because right, n plus 1 to the first times n plus 1 to the n, you would add those powers and get n plus 1 to the n plus 1. Now let's cancel a few things. The n factorial divided by n factorial is 1. And the n plus 1 divided by n plus 1 is also 1. So what we're left with is the limit as n goes to infinity of n to the n over n plus 1 to the n. Here's where things are going to get a little bit dicey. We're going to combine these together, kind of like we were doing with when we had like n plus 1 to the 4th over n to the 4th. We wrote it as n plus 1 over n all to the 4th power. We're going to do the same thing here. We're going to rewrite this as the limit as n goes to infinity of n over n plus 1 to the nth power. And the limit here is not going to be 1. So even though the insides are going to 1, getting closer and closer and closer to 1, that exponent up there is getting infinitely large. When you have something that's close but not actually equal to 1, raised to a larger and larger and larger power, there's a balancing act. Sometimes it gets really, really big. Sometimes it actually ends up going to 1. And sometimes you end up somewhere in the middle. And we're going to end up somewhere kind of in the middle here. Here's how we usually do this to make it easier to see. I'm going to write this as, I'm going to write this as the limit as n goes to infinity of, how do I prefer to do this? I like to do it like this. N plus 1 over n to the negative 1 to the nth power. to make sure. So I want to make sure everyone's cool with that, but I want to make sure Heather, does that seem reasonable what I've done there?
Yeah.
Okay. And then, so the reason I've done that is because I want to simplify n plus 1 over n as n divided by n plus 1 divided by n. So that's why I've written it this way. And then the power to a power will actually multiply out and write it as negative n. So we're going to write this as the limit as n goes to infinity of n over n plus 1 over n raised to the negative 1 to the nth is raised to the negative nth power. Okay, a couple more things. I'm going to rewrite this as the limit as n goes to infinity. Instead of writing this stuff to the negative nth power, I'm going to write 1 over that stuff to the positive nth power. And I'm going to simplify the stuff. Instead of writing n over n plus 1 over n, I'm going to write 1 plus 1 over n. And now I'm going to remind you of something I think I said a while ago, like many classes ago. The limit as n goes to infinity of 1 plus 1 over n to the nth power is e. So this limit ends up being 1 over e, which is notably less than 1. So this series converges. By the ratio test. All right. I think those are all the good examples. No, let's call it there. We can stop. I know it's, yeah, it's fine. So ratio test, if you see something raised to the nth, well, I should say, if it's not already geometric, it's not a p series, the nth term test didn't give you anything. If you see either being raised to the nth power, or especially if you see an n factorial, usually that means you should definitely try applying the ratio test. Really, I mean, trying it doesn't hurt ever, because if it doesn't work, it doesn't work. Yeah, those are the times I would look to the ratio test. All right, all I got. See you Friday.